Hello everyone, I hope that you are having a great day. Welcome to the first lecture video for Unit 4. In section 4.1, we will learn about graphing polynomial functions. Now we've graphed a few very basic polynomials using transformations, but in this section we're going to learn about more complicated polynomial functions for which we cannot observe the transformations. In 4.1.1, we'll learn about properties of polynomial graphs. Let's go ahead and define what a polynomial is. A polynomial function has the form p of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus first power plus ... plus a sub 1x plus a naught, where n is a non-negative integer and the coefficients a sub I are real numbers. Now, I bet that's not the first thing that popped into your mind when we said polynomial. You are probably familiar with binomials and trinomials and polynomials with 4 or more terms, but this is how we express a polynomial in general. So let's look at the details and make sure we understand what's going on here. Each term in the polynomial is the product of a real number coefficient and a power of x. So all of the a's with subscripts in this expression simply represent real numbers. The subscript coordinates it with a superscript. That is, a sub n goes with x to the nth power. Now, the highest exponent that I can find in a polynomial is what we call the degree of the polynomial. So this is a degree n polynomial. The coefficient of our highest powered term is called the leading coefficient. And the term without an x is called the constant term. So notice this polynomial is written in descending order. That is, it goes from the highest power of x, then to the next power down. This pattern continues till we get to x to the power of 1, and finally x to the power of 0, or no x term on that constant term. The ... there simply means this pattern continues for any number of terms necessary to represent a polynomial. So let's look at some examples of polynomials. A binomial is a polynomial with 2 terms. So, for example, something like x squared plus 5. Or a trinomial, a polynomial with 3 terms, might be something like 3x squared plus 2x plus 7. In a polynomial, each term is composed of the product of a real number and some power of x. And the sum of all of those terms is what forms a polynomial. So again, the examples are a little easier to recognize than the general form. Now, the degree, the highest exponent I can find, has to be a non-negative integer. That's going to rule out fraction exponents or negative exponents. So let's make a note: no negative or fraction exponents. That also rules out radicals. So polynomials are actually pretty user-friendly. All of the things that generally give us trouble, negative exponents, fraction exponents, or radical functions, will not be involved with polynomial functions. Graphs of polynomial functions are smooth and continuous. Smooth means that there's no sharp turns, and continuous means I could trace the entire graph without ever picking up my pencil. There's no breaks, there's no jumps, there's no sharp turns. Again, they're pretty user-friendly. For a polynomial, the domain is always negative infinity to infinity. So here's an example of a polynomial graph. Again, if I trace the entire graph with my pencil, I would never have to pick my pencil up. There's no breaks, there's no jumps, there's no sharp turns. It's nice and smooth. So this is basically what the graph of a polynomial looks like. When we graph polynomials, we're going to be looking for some important information. First of all, I want you to notice that most of the activity in this graph occurs in the interior. We call this interior behavior. That's where the polynomial is twisting and turning, it's crossing the x-axis, it's hitting those maximums and minimums. It's crossing the y-axis. Whoops, that's probably right there. So the polynomial graph is smooth and continuous. The ups and downs occur in the interior, and then on the extreme left and right ends, that's what we call the exterior behavior or end behavior. So looking at this particular polynomial, once the polynomial finishes all of its activity in the middle, then it settles down and it does the same thing for the rest of the domain. In this case, we would say the right side falls, and we would also say the left side falls. We're going to be able to predict that just by looking at the graph. When we graph a polynomial, our primary goal is to determine the interior behavior. Where are the x-intercepts? Where is the y-intercept? Where are the turning points, that is the maximums and the minimums, the tops of the hills and the bottoms of the valleys? Once all of that is determined, then beyond that, the polynomial will exhibit end behavior, either rising for the rest of its domain or falling. Keep in mind when we graph a polynomial, the maximum number of x-intercepts an nth degree polynomial can have will be n, and we will always have exactly one y-intercept. So this is a basic introduction to polynomial graphs.